You ever just stare at your morning coffee and wonder about it? I mean, really think about it. You pour it, it's steaming hot, and if you just leave it there, it gets cold. It's obvious, right? But if you put that same coffee in a thermos, it stays hot for hours. The why behind that super simple observation? Well, that's where things get really interesting. It's the key to understanding how pretty much everything in the universe works.
So what's the deal? The answer isn't really about the coffee or the cup, it's about energy. It's about how energy moves around, how it changes from one form to another, and the fundamental rules that it always follows. The science that explains all of this has a name: thermodynamics. Okay, so to really get how energy works, we have to get specific. We can't just study, well, everything at once. So scientists do something clever. They draw a little box around what they want to study. They basically create their own little universe in a teacup.
And that brings us to the official definition. Thermodynamics is just a branch of science that deals with energy and how it transforms. You can think of it as the ultimate rulebook for energy, whether you're talking about a car engine, a star, or the chemical reactions happening inside your own body.
So let's use our coffee to break this down. First, we define the system. That's the thing we're actually interested in. In this case, the hot coffee. Then there are the surroundings, which is literally everything else: the air, the desk, the room, and finally, you've got the boundary. That's just the thing separating the two. You know, the cup itself.
And it all boils down to this incredibly simple little equation. The system plus its surroundings equals the universe, at least for the purpose of our little experiment. Once we've defined these three things, we can start asking some really smart questions about how they all interact.
So how does this actually help us with our coffee problem? Well, it turns out that boundary, we just talked about, is the key to the whole thing. The type of boundary is what decides if our coffee gets cold or stays hot. And it really just comes down to three types: open, closed, or isolated.
Think about our normal coffee mug. That's a perfect example of an open system. Heat, which is a form of energy, is just pouring out of that cup into the cooler room. And at the same time, you can see the steam rising off the top, right? That's matter escaping. So both energy and matter are crossing the boundary.
Now, what if we put a lid on it? Just like that, we've made it a closed system. The lid stops the matter, the steam, from getting out. But the cup itself still feels warm, doesn't it? Of course, that's because energy, as heat, can still get through the cup walls into the surroundings. The coffee is still going to get cold, maybe just a little slower.
And that brings us to the hero of our story, the thermos. In science, we'd call this an isolated system. A good thermos is engineered with a vacuum seal and a super tight lid to stop both energy and matter from escaping. It creates this tiny, self-contained universe for your coffee. And that's it. That's the solution to our puzzle. The thermos works because it's an isolated system.
So here's a super simple way to look at it. An open system lets both mass and energy through. A closed system says no to mass, but yes to energy. And an isolated system just says no to both. We're just adding more and more restrictions to that boundary, and that's the first step to controlling energy.
Okay, so we figured out how to define our system. But how do we describe what's going on inside it? We use what are called properties, things like temperature or volume. But here's the catch: not all properties are the same.
Let's do a little thought experiment. Imagine you've got a block of something, say a chunk of iron. It has a certain mass, a certain volume, and it's at a certain temperature. Now, what happens if we chop that block right in half? Well, the mass of each piece is now half of the original, right? But what about the temperature? The temperature of each half is exactly the same as the original block. See? Different properties behave differently.
This difference gives us two new key terms: extensive and intensive properties. Extensive properties are the ones that depend on the size or the extent of the system. Things like mass and volume. Double the stuff, you double the property. But intensive properties are totally independent of how much you have. Temperature, for example. It doesn't matter if you have a drop of water or an entire ocean, the boiling point is still the same.
So let's just run through a few more examples to make this stick. Extensive properties usually answer the question, how much? Total mass, total volume, total internal energy. Intensive properties, on the other hand, answer what kind. They describe the nature of the substance itself, like its temperature, its pressure, or its density.
All right, describing a system in a single moment is one thing. But what we really care about is when things change, like our coffee cooling down over time. And to understand change, we have to make a really important distinction between the journey and the destination.
I absolutely love this analogy because it makes this idea so clear. Think about hiking a mountain. Your starting point at the base and your ending point at the summit, those are your states. But how did you get there? Did you take the super steep, direct trail or the long, scenic, winding one? That's your path. Your change in elevation is the same no matter which trail you took, but the actual distance you walked could be totally different.
So, in the language of thermodynamics, a property like your elevation is called a state function. All it cares about are the start and end points, the destination. When our coffee cools from 90 degrees down to 20 degrees, the change in temperature is a state function. It doesn't matter if it took 5 minutes or 5 hours to cool down. The initial and final temperatures are all that matter.
But what about the path you took? The journey itself? Well, those are called path functions, and the two most famous path functions in all of thermodynamics are heat and work. The amount of heat your coffee loses or the amount of work a system does absolutely 100% depends on how it gets from state A to state B. For path functions, the journey is everything.
This graph makes it perfectly clear. You've got a starting point and an ending point. To get between them, you could take the direct path or you could take this long, squiggly path. For a state function, like pressure, it doesn't make a difference. The overall change between the start and the finish is exactly the same no matter which way you went.
So I know we've covered a bunch of new terms here, but these aren't just random vocabulary words to memorize. They are the absolute fundamental building blocks. This is the grammar and the vocabulary you need to literally speak the language of energy.
So let's put it all together. First, we define our system and its surroundings. Then we figure out if that system is open, closed, or isolated. Next, we describe what it's like using extensive properties, which depend on size, and intensive properties, which don't. And finally, when things change, we track them with state functions, the destination, and path functions, the journey.
And once you have this language, you can start to describe and predict how energy is going to behave absolutely everywhere. And we're not just talking about cups of coffee anymore. This is the foundation for understanding everything from jet engines and power plants to climate science and the very beginning of the universe.
So, we've learned the words, we have the language. But every language has a grammar, a set of unbreakable rules. So the big question left is, what are the fundamental laws that energy must always obey? That's what we'll get into next time.